Hello. I wanted to make an announcement. In my talk this morning, I mentioned a paper by Freeman Dyson that was published in 1963. And some students have asked me about that. So if you're a student or a postdoc and you're interested, come here in this room tomorrow for lunch. Bring your lunch with me, and we'll go through the paper. It's a 5-page paper. And so come here and we'll read through Dyson's paper together. I'll put it up and we'll literally go through the entire paper from beginning to end. If you haven't read the paper, this is a chance to read it. It's really a nice paper. And I think Ajith is going to find someone to help organize that. But anyway, the idea is just come here at the lunch break tomorrow.
Okay, so let's get started. I think let us first start with the questions that someone could not ask during the previous session due to time constraint. So I think both Emanuele and Sweta is here. So if you have any questions, you can ask for them. No, I mean, they're online, but yeah, for Tanya also.
I have a question for Bruce, sorry. Is this the gravitational machines paper? Okay.
Yeah, yes, Dyson 1963 interstellar communications. You know the paper?
I was wondering if it was the one about gravitational machines.
Yes,
or
yes, that's the paper.
Okay, very nice. Thank you.
You know the paper?
Yeah, it's very nice.
Okay.
So any questions?
Yes, so I have a question. It's particularly towards Professor Bertie. That can you please tell us more about this phenomena of avoided crossing and eigenvalue repulsion? What I'm mainly interested to know is that what kind of systems exhibit this, and for a curved black hole, does this mean that for some value of spin, we expect to see the fundamental mode becoming equal to the first overtone, and what kind of observational consequences that may have?
So let me, I gave a talk on this at the Amaldi meeting, I believe. So I'm trying to look for the slides so I can actually use some plots to explain what I have in mind. Let me see if I find it. Yeah, okay. I found some plots. So let me share. Let me share this if I can do it. Okay, I'll just share my full screen. It's a bit risky, but so this eigenvalue repulsion story. Sorry, I'm trying to share. Okay, and I will share this. You see the slide? Now, let me start from here. So what happens is that when you compute the spectrum for curved black holes, if you take the co-rotating modes and you look at the frequency and the imaginary part as a function of spin, at some point you discover this very strange thing that was first noticed, as far as I know, by Onozawa in a paper in the mid-90s, that the n equals 0, 1, 2, 3, 4, 5 mode has this very peculiar behavior. And for a very long time, I honestly didn't understand why this was happening. Then there were some papers by Oscar Diaz and George Santos in Cambridge that noticed similar phenomena in Carl Newman. But then the paper that really clarified what was going on for me was this paper by Hayato Motohashi, where he looked at the excitation factors for these modes, and he basically used very well-established notions in the theory of non-Hermitian quantum mechanics to point out that what is going on here is an avoided crossing between the mode with n equals 5 and n equals 6. So when these two modes have an avoided crossing, the corresponding amplitude of the modes as measured by the complex excitation factors shows this very peculiar behavior where the amplitude of the modes blows up, okay? And what they pointed out later is that similar avoided crossing phenomena can happen when you have theories like Einstein-Maxwell axiom, where you can compute the scalar electromagnetic and gravitational perturbations. And even if your black hole is non-spinning, then you can have avoided crossings between modes of different classes. So what you see here is an avoided crossing in the gravitational sector between the overtones with n equal 5 and n equal 6, which presumably we'll never be able to see because these overtones are very highly damped. But in this Einstein-Maxwell axiom theory, the paper that they wrote is the one down here. What they observed is that the fundamental modes in the gravitational and axial, gravitational and axion and gravitational electromagnetic sectors can have avoided crossings for the fundamental modes. Now, I find this particularly interesting. We also wrote a paper recently that I didn't have time to discuss, but so let me explain. There was another paper by Cavalcante, Mauricio Richards, and others, where they considered instead massive scalar perturbations occur. And what they found in this paper is that instead of having avoided crossing, you can have the exact crossing of, in this case, the fundamental and first overtone of bounded massive scalar perturbations. So what you see here is that you start off with one of the modes, say n equals 0, and then there is a very special combination of masses and spins. The spin actually here is nearly extreme, it's something like 0.999 or something like that. And for a certain value of the mass of the scalar, these two modes cross exactly. Now, this cannot happen for massless scalar perturbations, but in the case of massive perturbations, you have two parameters. And what they found, interestingly, is that this corresponds to a phenomenon of hysteresis. So you start off from here, and if you track your mode in this direction in the mass of the scalar field versus spin plane, and you go over here, you find that you are still tracking the fundamental mode. But if you go from here to here, you find that you go from the first mode to the overtone. So the actual value of the mode frequency that you find depends on the path that you trace in the mass of the scalar field versus spin of the black hole plane. And initially I was very puzzled by this, but then with this Chinese student, Yi Chu Yang, what we understood is that basically what happens is that you have two Riemann sheets, and when two modes agree exactly, then you are basically at a branch point. And as you track the frequencies in the complex plane, you are shifting from the first Riemann sheet to the second, and then back again. So basically, if you were to circle this path twice, you would go back to the original mode. Now, all of this is interesting because whenever you have these exceptional points, your waveform picks up an actual resonance. So instead of having a superposition of damped exponentials, you also pick up a linear in time term. And what we also proved with a simple toy model is that if this linear term is actually present and you try to fit only damped exponentials to the signal, you will not get the right frequencies. So in principle, depending on the damping time of the perturbations and the strength of the coupling between different modes, these things could be observable. Was the answer clear enough, or? I can go into more detail, but I don't want to take too much time.
So, hi, Manuel. So in one plot, you showed the different PN orders and what are the deviations from it through PPE. And in that plot, 0 PN, 2 PN, and 3 PN had a lot of errors, like it was like very wide. So I was wondering what is causing this deviations in the 0 PN, like at the leading order, why still there is a scope for some uncertainty at the 0 PN order itself?
Are you talking about the LIGO violin plots?
The violin plots which you showed for PPE.
Yeah, let me share the other presentation then. So, well, but I can say those violin plots were not the state of the art. They were violin plots from the 1509-14 tests of GR. And now those got a little bit better. But the point is that the specific constraints, first of all, let me say that I'm very skeptical about attributing any meaning to violin plots that are obtained in that way, because what you're doing is you are effectively fixing all of the other parameters in the SPA expansion, and you are only modifying one of them. So I don't really believe too much into any constraint that is found in that way, because you should consider correlations between different parameters, and we know that in GR all of the PN coefficients are correlated. So this is a test that you can make, but I would be very careful in attributing any meaning to those violin plots. Two comments. One is that typically the strength of the constraints that you get depends on the masses of the system that you look at. So if you have very few cycles, for example, then you're not going to constrain the low PN coefficients and vice versa. So that's one of the effects that enters into the particular violin plots that you observe. And it's not too surprising that when you go to very high PN orders, you don't get very strong constraints because, you know, just there is not enough signal to put any constraints. And then, yeah, there have been attempts at modifying these tests, for example, by introducing this parameterized DOB approach. In general, I'm a little worried about all of these parameterized tests where you introduce phenomenological parameters and you get certain deviations. There was a very, probably some of you were on that paper, there was this 230814 system, which had a single detector SNR of about 40, in which if you look at the same violin plots, you will see that for some of the PN orders, GR is actually violated. And, you know, if you look at the paper, they say quite clearly that they don't believe that these are actual GR violations. It's just that with a single detector and no constraints on the inclination and the sky location of the source, it's very difficult to perform tests. So I just want to invite everyone to be very careful when you look at these tests and their strength, or even violations of GR may not actually be violations of GR. It could just be that we should do the tests in a much more careful way.
Yeah, hi. My question is for Emmanuel and Tanya. So when you guys considered these modified theories of gravity, where you add to the Einstein-Hilbert term some corrections at the fourth order, I guess, in derivatives and so on. My question was, wasn't that this result that if one looked at Shapiro time delay in these theories, then one that leads to a Shapiro time advance instead of a delay, and so on the grounds of causality, these corrections should not, I mean, they may not be viable, at least. This work of Maldacena, Zebodev, and Edelstein, and so on.
Tanya, do you want to respond? You want me?
What were the theories as such? Were these the theories, or?
So there's a theorem. I actually had the paper somewhere there. There's a paper by Camagno and others. Camaño is the first author, but Maldacen is on the paper where they point out that on general grounds, you will not be expected to see any deviations of GR in gravitational waves, because for most of the theories that you consider there, the EFT theories that I was discussing, if there are any corrections, they should already appear in things like the Shapiro time delay. It is, in principle, true. And there was a paper recently by Nico Younes, however, where who was on the paper, Stefan Alexander, Nico, and others, where they argue that, in fact, the causality argument that rules out these theories is an expansion on flat space-time. So the argument in the paper by Stefan and Nico is that when you consider tests of GR, you should not be expanding on flat space-time, and so those arguments do not hold. I have to admit that I didn't read the paper by Stefan and Nico carefully enough to have my own opinion on whether they are right or not. But if you want, you can send me an email and I can point you to Nico's paper.
Yeah, can I ask something related to this? See, in scalar tensor theories, there is always this issue of Jordan and Einstein frames. So what kind of differences do you expect in, it's a question to both Manuel and Tanya. You have used scalar tensor theories to a large extent in your work, right? Or what you talked about today.
Tanya, you want to take it?
Is there any comment you have on this?
Yeah, I mean, in principle, one can transform between frames as well. And it's known how to do it. Yeah, ultimately, if you have exactly the ultimate observables, they should be independent of the choice of frame. But yeah, then it requires really going all the way to the observed signal, tracing how the detector responds, depending on how you formulate the theory and so on.
Emmanuel, do you have any comment on this?
No, that in principle, as long as you do the transformations carefully, there is no difference at all in the observables.
They will be different. The results will be different, right?
No, they should not be. If you consider gauging variant observables, doesn't matter what frame you use to do the calculation.
Hi, so I maybe just have a comment. This is David. So I agree that if you go from one frame to the other, it's equivalent. It's more about how you set up your theory. So if you set up a theory with black holes, I believe that you often basically consider that you are either in Einstein frame or Jordan frame, but you don't really care because you don't have any matter. So you don't have a matter action. And then when you start modeling these point particles as matter, then the question enters. So I think there might be some subtleties at that level, some choices, which is essentially a choice about the theory you're making, which doesn't matter when you're only dealing with black holes. But yeah, if you have a neutron star, for example, you have to think about it. So I wonder if you have any comments about that.
Because there are some theories which do not have a Jordan frame, which are called no-Jordan frame theories. And there's a classification. It's called a type 1 and type 2 classification, which has come up recently in the last few years in some papers. I think Mukoyama and people like De Fellis have made this classification.
I just want to comment on what David said, which is correct. I mean, they're both correct. So the difference only appears in the presence of matter. So it depends which metric do you couple your matter minimally with. So it's whether the Einstein frame or Jordan frame. But once you choose your theory, you're allowed to do the calculation in either frame and you should get the same result. So if you have a theory in which matter couples minimally to the Jordan frame metric, when you transform to the Einstein frame, matter will be coupled conformally, not minimally. But if you're consistent, as Emanuela said, you'll find always the same the same result. But you have to specify the theory first, including the coupling to matter.
Any other question? Rajesh. Rajesh. I have a question to Tanya. You discussed about the charge-induced scalarization for neutron star. Are there also models for spin-induced scalarization for neutron star? I know there are some models for black hole scalarization which are spin-induced.
I will have to look up the reference. I don't know off the top of my head.
That will be like more.
Knows or Emanuele?
Sorry, can you repeat the question? I'm pretty tired. I woke up at 4.
So, I have seen some models which are talked about the spin-induced scalarization of black holes. But
Right.
Tanya talked about charge-induced scalarization of neutron star. I was just wondering that whether such models are also available for neutron stars, which are spin-induced, not charge-induced. Yeah.
Spin-induced scalarization in neutron stars.
Yeah.
I don't remember, honestly. It's possible that someone thought about it, but I don't remember seeing papers of this. There was some work recently. I'm not sure. The answer is I'm not sure. I will have to look it up. But Raisa Mendes maybe did some work on this. I'm not sure.
Yeah, Emanuele, you mentioned in your talk that so larger black holes have smaller curvature, and hence, it's like, but we can measure the black hole ring down for larger black holes better than smaller black holes, and so you can't really probe length scales which are relevant or something like that. I don't know if it was you or somebody else.
Yeah.
But then for the in-spiral test, it should go the other way around though, right? I mean, if there is, and so, and like you can measure these lower order PN coefficients really well. And so
Yeah, you're
you
right.
can set up those tests pretty well and measure these.
Yeah,
lengths.
so in fact, you are completely right. So what happens is that if you go to low masses, then you would expect to constrain dipolar radiation much better. And what I was saying is that ring down only tests look quite hopeless to me because the bounds on the coupling constants that you can get from ring down alone are always going to be worse than the bounds that you get by not seeing dipole radiation in the in-spiral. So for binary black holes, the in-spiral bounds will always beat the ring down bounds.
Okay, thanks.
And also another person who might have worked on spin-induced scalarization is Daniela Doneva, but I will have to look at their papers. I know that they did a lot of work on neutron stars in modified gravities of this kind. So Daniela and Stoichko, Yazadiev, or Raisa Mendes, if they have done some work on this, it would be them. To go back to the previous question, sorry.
Hi, I had a quick question. So I sort of missed the neutron star coupling with the scalar field coupling with the neutron star matter. So is it a minimal coupling or how it was done? Very briefly, if you remember.
The theory I discussed.
Yeah.
Yes, so, well, I wrote it down in the Einstein frame where there's the conformal factor in front of the metric couples with the matter. And the metric, yeah.
Okay. So it doesn't distinguish between which type of species you are kind of considering, just the whole optim uni part, it couples the matter?
Yeah, it's that the conformally rescaled metric couples to the matter, but that conformal rescaling depends on the scalar field.
Mm-hmm.
So there are a few questions which Professor Shankar and Krishnendu, they have shared with us. I will just go through them. So this is regarding the violation of GR. So the question is, how can we confidently distinguish a genuine violation of GR from false indicators arising from source modeling uncertainty, noise modeling error, and unaccounted astrophysical effects? So like if we see some signal which says it is not explainable with our current model, when will we be able to say that it is beyond GR? And I mean, like any guess about what time in the future we'll have that certainty that we know all the astrophysical aspects and other uncertainties pretty well. Just as a broad discussion, if anyone has any comments, I mean.
Yeah, hi, Chishman here for people in the on Zoom. So actually, one thing I want to point out is a paper led by Anuradha Gupta and several other authors. I guess many people are here as well. They come up with a list of possible violations from GR, which come either from the waveform sector or from the detector, so detector glitches and or from astrophysics. And that's a good place to look into all the possible problems. They do not list the solutions, but for solutions, some of us are also thinking of if we detect a possible violation. So our first hunch would probably be that it's a glitch. So you do similar injections in various different data stretches to see how often such a false violation comes up, that we get an estimate of the background. So this is with regards to detector and waveform systematics. There'll be people who are more experienced in the audience who can give you a set of tests for waveform systematics as well. For astrophysics, it's a bit more complicated because environment has certain effects, but still all of these are not fully exhaustive. So I don't know. This is just some things that I want to add.
Just a very short comment on that. I think that's probably the right approach, but one way I would think about it is that any sort of violation of GR that is like you would expect it to happen in all the events. Maybe in certain events it's slightly more, in certain events it's slightly lesser, and that could also be, for example, propagation-based violations. So if events are very far away, it's more. If events are very close to us, it's lesser. But I guess one thing that one can look for is you can utilize power in numbers. So if you stack up a lot of events together, then these glitch-induced violations then go away eventually. And what you're left with are violations that are either systematic because your waveforms are not good enough, or they might actually be true to some extent. So maybe stacking up could be a way to mitigate some of these issues, but definitely not all of them.
Yeah, just to take it forward from there, I'm just wondering, once again, the same argument, the ubiquity of whatever theory of gravitation is out there, it should also affect EM observations in other astrophysical phenomena. So I would imagine then that whatever violation that we have found or apparent violation that we have found in GR, that should lead to some other consequences that is verified elsewhere. Do you think that's a fair comment?
Like Tanya, I mean, in your case, if the scalar field also couples to electromagnetic F mu nu, I mean, which it will because it conformally couples to T mu nu, or some other field which is present, do you think that will change the picture?
So that, I mean, I can't say off the top of my head or calculate in such a short time, but yeah, so I agree in principle, yes, it's good to look for correlations between electromagnetic signal deviations and those in the waveforms. But I think given the plethora of theories out there, there might also be theories that could evade anything you can observe with electromagnetic tests. So that's maybe, yeah, just something to consider.
Yeah, I think, Urtishman, you were talking about metrics described by the PPN parameters. Is that the way you're changing? No. Or you're talking about metrics in different theories with different parameters? Okay.
Just one comment. I heard Enrico before. I don't know. I think he's actually there. But Rohit and Enrico have a paper recently on distinguishing astrophysical effects from beyond GR effects based on the idea that Ish was discussing, that all of the GR effects, beyond GR effects, should appear consistently in all of the events, while the astrophysical modifications will be different on a case-by-case basis. I don't know if Enrico is still around and if he wants to comment on this. We read the paper at the Journal Club last week.
Who made that comment? It was Ish Gupta who made the comment. Nico is not here.
I thought Enrico was talking just earlier about the Jordan versus Einstein frame issue. But anyway, there's a paper by Rohit Chandramouli and Enrico that does exactly that.
Yeah, the paper is by me, Enrico Emanuele, but not by Rohit, Alvin Chua and Shubhankar Rijiwal, the three of us.
Sorry, I thought Rohit
yeah,
was
we do
also
exactly that. We try to take astrophysical catalogs for MRIs and try to come up with compute odds ratios between different hypotheses, modified GR, environmental effects, and vacuum GR. Turns out you can distinguish if you have about from 10 to 100 MRIs.
That's a lot, but okay. Yeah, we saw the paper. It's interesting. The formalism is very interesting. It can be applied also in other.
It's almost the end of the day, so I thought I will make an interesting comment. So I don't work on this and don't understand the full degeneracies between different parameters and so on. But the way what I understood is that once a real deviation is detected, I think everybody will be fighting to say that, oh, this is probably eccentricity. Somebody will say this is a violation of GR, and somebody will say something else. Is that going to be the situation, or it is going to improve with like the next generation, or even, even with the present generation with let's say 05 and so on? Has anyone like done real injection studies to see that whether this sort of degeneracies can be broken?
Hello, this is Frank for the people online. I think the situation you describe, we're already in to some degree. I mean, if we look at some of the events, I don't know, 1905-21 is the first one where this, it's exactly as you say. Someone says this is a head-on collision, other says a boson star, this is eccentricity. And while, of course, this can be a bit frustrating, I think this is exciting. And I think no matter how hard we do, there will always, hopefully there will always be an area where, enough clear research will eventually, a clear answer will prevail and some others can be ruled out. But as we dig deeper and deeper, as we always will, there will always be this gray zone where this is plausible, this is not plausible. And I think it's an interesting question. How do we resolve this then? And we had this earlier. I think then only time helps. Seeing the same thing again with higher confidence on this might help. But I think individual events will always lead to these type of debates.
Like in principle, can the degeneracies be broken, or we need something else, some other measurements to break the whole degeneracy? In some situations, like mass redshift and things like that, it's probably very difficult to break those degeneracies. But here, is it possible to break it with infinite, let's say, with 1000 SNR? Can one break the degeneracy?
I hope the answer is yes, but I'll let others speak.
I think you will have to look at other observations, not just in GW. And cosmology probably can show you some way for selecting the theory. So it has to be compatible with all kinds of theories, right? All kinds of observations. One theory for all kinds of observations. That will be the indicator to select the theory, which is the theory, which explains a large number of observations.
No, I think I mean, just wanted to say it's possible. And also with high SNR and good models, you can actually see the difference, right? I mean, when you used models without higher modes and using with higher modes, how this changes. Also low SNR to high SNR, how it would change. So I think breaking this degeneracy is visibly clear from like last few years itself. And it is possible, I think.
Can I add another point to this? Yeah, so the question is also what kind of degeneracies are you looking at and what deviations you get. For example, if you get a smoking gun effect, for example, you see a mode that you are not expecting, or you see the presence of a scalar mode in your tensor sector, for example, then it is something that you can concretely say about the deviation. That's one thing. And the other thing I do want to comment was on, I don't know, someone suggested about stacking events. And that is actually a little bit more tricky. For example, we're already seeing in ring down in the LIGO observations that when you stack, you do see some sort of spurious deviation because stacking also stacks all of your systematic errors. So that's something that you need to be more careful about compared to like the golden events that you get.
About stacking. About the stacking of events, it's sometimes you just stack all the systematics as well. So so if you had a very high SNR event and one TGR estimate versus maybe the entire stacked posterior, maybe the single event can really give you a better unbiased estimate compared to the stacking. Also, I think it depends on which method you use to stack. So yeah, it's
Sorry. Yeah, I just wanted to make this comment. I think in case of neutron star equation of state and with the confusion with the this is scalar field with coupled with gravity, I think it may be possible if you know so you have some measurement with say heavy ion collision and things like that where the gravity is not important, but you have the similar type of matter composition. There you can try to infer some equation of state parameters that you can tell you with the whatever measurement you have from astrophysical observations where of say tidal deformability and things like that, where gravity is more important and your scalar field will come up in this part and not in the other part. Do you have any thought about it or anything?
Yeah, I think in principle it's a good idea to try to maybe get the equation of state from other means where the scalar field is not so important. In practice, yeah, it's of course still a long way to connect from heavy ion collisions down to regimes probed in neutron stars of matter. There's still, for instance, the heavy ion collisions are completely dominated by kinetic energies, whereas in the neutron star, it's really ground state multi-body interactions. So yeah, I think one should try, but probably one cannot completely resolve it in this way.
Since there was a comment that if we had access to a very instruments with a very high signal to noise ratio far into the future, and if we can do something to break the degeneracies, which I assume is in the ring down signal, then we know that even a slight modification to GR produces a significantly different late time tail. Like adding a small cosmological constant will change the behavior of the late time signal or a massive scalar field. So if we can actually measure somehow the late time tail will not that help us distinguish between various theories of GR or even between various alternatives to black holes and all?
Any of you want to answer that? Okay.
Well, maybe I can just comment that we haven't been able to see tails even in the GR simulations that we have at the best resolution that we have. There's only a few recent papers by Shijun Ma and others where using Cauchy characteristic matching, we start seeing the tails in GR. Now talking about seeing or not seeing the tails in actual data, given that we have a hard time seeing them at infinite SNR in the numerical simulations, in principle it can work, but I'm not betting my retirement on it.
I think, Apratim, you have raised your hand. Maybe you can go ahead and ask a question. Unmute yourself.
Yeah, thanks, Sudipta. So this is for all the ring down experts in the panel. I just wanted to know, at what point in the future are we going to resolve the issue between when to start the ring down analysis to that of whether it's an overtone or not? Do we have, can we really do this at any point?
If I can go for this. So in principle, I would say that because this degeneracy, whether or not it's an overfitting is a very hard problem to say concretely, in the sense that mathematically it does fit, right? And so that means that even in an infinite SNR limit, you can always see the support for overtone, as long as you have a loud enough signal and as long as you go early enough. However, this doesn't necessarily mean that you can physically interpret them as overtone in any concrete manner, right? I mean, that's exactly why this debate is probably going on for a very long time now, because it's hard to say. It looks like, at a fundamental level, you do expect that merger and close to merger dynamics have nonlinearity, and you see this in things like head-on collision, as in the sense of seeing the second order correction required in the ring down. So you would expect that to be there. And so I guess in terms of the answer to this question, I guess my personal take would be just wait for long enough that you see an angular mode before you claim spectroscopy as a concrete test of spectroscopy, because we're almost there anyways. We are already seeing ring downs with an SNR of 20, 25. I guess a little bit more you'll be able to see. For example, the new event that you saw, 250114, it was lucky for ring down only in the sense that it was loud. In all other manners, it was an extremely unlucky system. It was an equal mass system. You barely had anything else. If you find once a system with, say, mass ratio of even 2, you will be able to do a concrete angular mode spectrum anyways. So I guess we are at a point where you can ask the question of, do you believe in overtone or not? But you are going to get a spectroscopy for where you can do a concrete angular mode spectrum. This is my personal take again.
Thanks. But also, about this recent sort of overtone sort of claim for 23, 10, 28, right? So I don't know. Do you have any comment for that?
Yeah, I mean, I've been in the for a paper writing team, so we've been discussing about this quite a bit. And I think it's nothing has changed from what was happening with GW150914, except that this is a slightly louder signal. And yeah, that's about what I would say.
Yeah, so I was wondering that even if you get a 1000 SNR signal, there can always be some other terms which we don't have in the current waveform, which would become important. So always, even if you find a deviation, you can always attribute to some extra terms which may be missing, some higher PN or something else. So how sure we can be that, because the waveform systematics itself may not allow us to conclusively say that we have a deviation from GR, right? Like from waveform modeling side, when we can be prepared that a waveform is ready now, we can just go and find a deviation and we can clearly conclude it. Yeah, it's to the panel.
Yeah, can I add just one point? So addressing that question about ring down, which Apratim asked, I think one needs to understand the merger dynamics. And for that, we need to build models for the merger. Analytical ones are very difficult, but semi-analytical and numerical models of the merger are necessary. Then only we will know when the ring down exactly starts. Otherwise, I don't think we have a chance.
Just to add on to this comment, if you don't mind. So the problem with this is like we do have numerical evolution to track the mergers, right? But the problem is it still is that the mapping between what's happening in the source frame to the points on the waveform, that's a problem, right? Because when you're doing, for example, a waveform extraction, you can't basically you can't associate a particular dynamics in a strong field region to a particular point of the signal that you see. So it is what you're saying is absolutely something that I do believe in, that we need to understand merger dynamics better. But even with that, there is a problem of trying to associate what happens in the merger dynamics to the waveform, which I think is kind of a bigger bottleneck at this point that we have.
So it's a sort of related question to the discussion that's been going on right now. So how badly are we affected by the fact that we don't have cutting edge beyond GR numerical relativity waveforms? Is that a big problem, you'd say?
I don't know the exact answer, but I think it's also like which theory you're looking into. There are a lot of models, and I'm not like, so I think so far from the theory agnostic test, it's very hard to say if you really had a model, what would have been the implication, right? Like, I'm not sure, like, if you know the full answer to that, like, also in terms of taking a full modified GR waveform model and analyzing the real data and see, like, what would be the measurement for that. So I think it's like a large number of models, and there is not much large that many of studies which we can really talk about or say anything about this question is what I think, but I don't know if others can add.
No, I mean, don't you think that, or is it fair to say that our best chance of perhaps seeing a violation of GR is in the most dynamical nonlinear regime? And therefore, having numerical relativity waveforms become all the more important. Do you think that's a fair comment?
I think so, yeah. Also, I know for the boson stars, for instance, the simulations are really useful. I mean, at least to, we can really learn more about the full simulations, including the measure of exotic compact objects. So I think it's so, I'm more used to, I'm more exposure towards that, but I haven't used, for instance, modified GR models, but I think at least from the exotic compact objects perspective, it's really useful to have a full model, yes.
Uh, I wanted to bring a different perspective or along the line of history of science, following Thomas Kuhn. So like when I see the shift from Newtonian to general relativity, actually for Einstein himself, it was sufficient to see the perihelion of Mercury. He was just excited about that, and he was certain that his theory is correct. Actually, and Eddington suggested about gravitational redshift test in 1925, which was actually observed and tested. But that was also not sufficient for the community. It was actually bending of light, as far as I understand, which was the completely new test, which actually told us that, okay, which is completely not predicted by Newtonian laws. However, there are ways you can do that, bending of light, but I think we have to also bring that perspective that there is some sociological aspect as well. Similar thing happened at the time of Clifford Will when he was doing PPN tests, and like thousands of theories, not thousands, but at least tens of theories with different types of formalism came, and he tried to show in the Bayesian formalism that why GR is the correct one. But I think, so that was my comment. Like we need to, probably the best test should be that anyone working on alternative theories must come up with a test or prediction which is not which does not happen in GR at all. That would be the first and confirming, and otherwise we'll keep chasing with all these environmental and other effects. And of course we can do it in Bayesian way, keep accumulating evidence, and that will happen. So just wanted to bring this. Thank you.
So you want to see something in the observation which is not explainable in terms of GR. Yes. Is that what you mean?
Yes.
So the deviations which are not in GR, I'm sorry, they're predicting something which is not basically in GR. The thing is that these deviations vary as a function of parameters or whatever your theory, blah, blah. And the second thing is that the way I understand is, let's say if you detect a signal, right? So we have to list down all the problem. I guess everybody knows, right? Like, okay, whether we are missing physics, maybe it's eccentricity, precession, or maybe some astrophysical microlength. I mean, if we detect a deviation with certain probability, I think optical depth microlensing will be of the same order. I don't know. One can say confirm it. So this is just one effect of astrophysics. There could be like accretion risk, but so maybe it's possible to list down all the problems. But question is whether at what SNR really the differences in the predictions basically start coming up. But your question is, but I guess everybody is focusing on only those theories, which basically predict something different. But
Yeah,
magnitude, of course, depends. And
yeah, thanks. I think let us go to the final question because we are almost ending. So I think one of the main question that was suggested by the Professor Shayan Kaur is that with the arrival of next generation of gravitational wave data, what are the primary challenges in testing general relativity? So like, I mean, if we get a very high signal to noise ratio data and all that, what are the main challenges that one might face in order to say that whether GR is correct or not? I mean, like if you envisage it from particle physics perspective, like you have a LHC which cannot detect beyond standard model physics, but then you build higher LHC runs and you can in principle continue because you do not know when you are going to see beyond standard model effects. Now, will that be true for gravity also? Like suppose we do not see anything in the next generation. I mean, would it make sense to go for, next to next generation and so on and so forth in order to make sense? And what should we look for really?
See, if you compare with particle physics, there is, beyond the standard model, there is this MSSM, right? Now, MSSM is based on certain observational facts, experimental facts. But the point is that it hasn't been very successful because it needs the existence of supersymmetry, and nobody has seen supersymmetry, right? So, but there is some logic behind the construction of MSSM. On the other hand, in this modified gravity scenario, there are close to 30 to 50 theories, all of different kind with different motivations. And large number of them deal with the fact that you want to resolve the singularities in GR. So one of the main motivations in construction of modified theories is to address the question of singularities in GR. That's why many of them were constructed originally. So now you have to pick and choose and work on each of those theories and find out whether they tally with certain observations, which is a very difficult task, as some of you pointed out, that you cannot just go on doing this. So there has to be some indication from observations which will tell you that you follow this direction. And we have to wait for that indication. Otherwise, I don't think just by looking at small scale deviations or looking at precision tests, you can discover something really new, if at all it exists. Okay, so that's my take on the subject. I think others can point out whatever they want.
So I will request all the speakers to let us know about what they think about it. Maybe starting with Emanuele and Sweta and then Tanya.
Okay, if you want my honest opinion, we're not building next generation detectors to see the third digit in the deviation of the quasi-normal mode frequencies. We're building them because we have a very strong science case in astrophysics, multi-messenger astronomy, searching for stochastic gravitational wave backgrounds of astrophysical origin. And then I would hope seeing stochastic gravitational wave backgrounds of inflationary origin. And that's the real reason to go forward. Now, if we see deviations from GR, and we see a smoking gun deviation from GR, I'm going to be the first to celebrate. But again, I don't think that's our strong selling point to the funding agencies. This is my very honest opinion. I'm in a session in which I'm talking about deviations from GR, and it's something that I'm very interested in, obviously, but I think we're going to keep testing GR with null tests better and better, and we'll find better and better agreement at the level of the astrophysical observations that we can make. And we have a very strong science case, but this is not the strongest science case for building better detectors.
Thanks, Emanuele. Maybe Sweta, you want to add it?
Yeah. So I think that, for example, the ground-based detectors, for most of, I mean, they will give us better SNRs, and you can do null tests better, as I mean, and I think it's kind of useful to state that you can do null tests better. And I think in some way it is, at least to me, it feels like it is mirroring the particle physics scenario, in the sense that you make it better and better, and you can constrain what you know, stronger and stronger, and hope for a deviation. The other thing I do want to say is that I guess one big thing that will happen with the next generation detector, or like going forward, is that we'll get different kinds of sources. Right now, we've been seeing a lot of almost equal mass mergers, and certain kind of tests, like for example, ring down test, right? We are kind of very limited in the sense that if you have larger asymmetry, you would have seen a lot more modes, but you've been seeing a lot of loud events that happens to be barely rotating equal mass systems, which are not really great for us to do a lot of tests of GR. So like one big thing that I am, at least personally, I am excited moving forward, is that hopefully we're going to see a broader variety of things with larger spin, with precession and stuff like that. So especially this is when you talk about supermassive black holes with LISA, for example, for testing GR, it becomes a little less interesting, especially for strong field stuff, because most of these effects will be inversely proportional to mass to the power something. But for example, for stellar mass black holes with either 3G detectors or LIGO with improvements, I guess it is promising. That's what I would say.
Okay, thanks, Shweta.
Yeah, I think most arguments have now already been brought forward. Maybe I can say, because you mentioned next generation detectors, but I mean, already we don't have next generation yet. And if they are built, they are supposed to be built for 50 years time. So I think within at least our professional working time, this will not happen. So that's just some addition.
Final comments from any participant?
I think
Maybe I can
Rahul has mentioned this. So I just make a comment about the history of science. So when this precision of Mercury was first detected, long before GR, when people know there is some anomalous precision which cannot be explained by interactions of the other planets.
There were so many other theories like extra planet, 10th planet, or some arbitrary corrections to the 1/r law. But then when GR came, we knew that it is the explanation. So my hope is that when we'll see a modified gravity signature, we will know it's a modified gravity signature. That's probably the hope. Let's see.
Yeah, for my perspective, I think like with Sheta, that the modified gravity theories are important because as and when you see deviations, and if you run out of your eccentricity, spin precision, and all possible orbital, uncertainties, then you need to have some model in order to test these things with. So it is better to have some people at least working on the backdrop, working on these topics. I believe that is important for the community. And the same is also true for this exotic compact object, because I completely agree that they are made out of some 5D object, negative energy density, and so on and so forth, which may not be something we would like. They may not be very physical, but at least at the end of the day, if you have only one theory, there is nothing you have to test it against. It's better to have, other models against which you can test. And who knows, like if luck favors, like LHC got the Higgs boson, maybe we could get some deviation from GR. Okay? So it's the hope that keeps us alive. So hopefully we'll meet again in 10 years with more progress. Thanks.
Okay, thanks a lot
for coming to this session.
So we thank all the speakers and all the panelists for the session. Thank you.